let's look at different types of polar equations and how they look on graphs. How might the polar equation r equals 1 plus cosine theta look on a graph? This is not going to be drawn to scale by any means, but it's going to look something like this. This is called a cardioid. What about the polar equation r equals 5 times cosine of 2 theta? This curve is called a four-leaf rose. Moving on, we have r equals 5 times cosine of 4 theta. How might this look on a graph? This is called an 8-petal rose. What about the equation r equals 5 times cosine of 3 theta? Well, it should look something like this, and now it's a 3-leaf rose. One thing that we might want to take into account when it comes to the roses and the leaves or petals that they have is the pattern of change. Let's look at the pattern of change for cosine of n times theta and sine of n times theta. If n is even, you're always going to get twice the number of leaves. So you'll get 2n leaves. And if n is odd, then you get the same number of n leaves. So for an example, if we have r equals 5 times cosine of 7 theta, that's going to be a 7-leaf rose. And what if we have r squared equals 4 times sine of theta? That's going to look like this. This here is called a lemniscate. I don't know if I'm saying that right, but this is the spelling for that. Lemniscate. And so these are a couple of different polar equations, but they're quite beautiful. Wait, am I recording? All right. What are polar coordinates? Well, we cannot talk about polar coordinates without talking about the Cartesian coordinate system, also known as the regular coordinate system or the rectangular coordinate system, um, which was discovered by somebody called René Descartes. René Descartes was laying in bed and he was looking up at his ceiling and there was a spider, and the spider was crawling all around his ceiling, and his ceiling it had tiles on it. And so he's looking up at the ceiling, and the spider is crawling, and the spider stops and chills out for a second right here at this point on the tiles. Renee figured that he would be able to describe to somebody where the spider was exactly, who was in another room, by utilizing the tiles. Thus, the Cartesian coordinate system was born. And here, where the spider is, that's point 3, 4. We'll put an R there for a rectangular coordinate system, such that 3 is x and 4 is y. Well, coordinates have different systems. You know, like when you think of like a radar screen, at least I think of green, and then I think of these, like the placement of these circles. They're concentric circles that move outwards. And as we make our transition from the Cartesian coordinate system to the polar coordinates, I'm gonna stick um, with this x and y axis, but it's not x and y anymore. Um, Polar coordinates are a little bit different. So here at the origin, this is still the origin. Um, this is called the pole. And we can mark the same point, the exact same point on our map right here. But the idea of how you get to this point here, it's like you're facing this way. You're facing this way. This is technically not the x-axis, but you're facing the x-axis, and say like you look up and you look up at that exact same point. All right. The distance from you at the pole to that point is denoted as r, but it's a lowercase r. and r is the distance. But what about how you got to that point? What's the angle between the x-axis, which is no longer really the x-axis, it's a ray, it's a line. Um, how did you get this angle here? And what is this angle? Well, that's angle theta. We have r is 3, 4, but in the polar coordinates, we have the point is denoted with p, and p is, well, and there should be a colon here, but p is going to be r theta. And let me just move this out of the way for a second. We'll get to that. We'll get to that, but I just want to be able to unpack this here. Let's try to connect these two mathematically. The rectangular coordinates are 0.34. The polar coordinate system, it uses r theta. So we're at 0.34, and let's say I drop a vertical line from 0.34 down to the x-axis. All right, and we'll do that down here. I'm going to drop a vertical line from our point to the x-axis. But now, at this point, I have a right triangle. So if we look at the bottom of the right triangle, from the origin, it branches out to about 3. Okay? And so what that means is that our adjacent side, our side that's adjacent to the angle that we're trying to find, namely theta, well, it's going to be right here. We know it can't be right here because that's the hypotenuse. So the adjacent side is 3, also known as the base. X equals 3. I just drew a line to connect the hypotenuse to the origin, just to be clear. This here is the height, but it's also the side that's opposite to theta, which what that means that it's the opposite side. OPP for opposite. If we count these little squares, we got 1, 2, 3, 4. So in trigonometry, the tangent of an angle is the ratio of the opposite side and the adjacent side. And we can remember this using the mnemonic device SOHCAHTOA. I did not make up SOHCAHTOA. I don't know who did, but whoever did, they came in clutch because watch this. Sine of theta equals opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. Tangent equals opposite over adjacent, which is exactly what we have. The opposite and the adjacent sides. We could say that this is y over x. So tangent is going to be 4 over 3. That's great. We have tangent of theta. But the problem is that we don't want tangent of theta. We want theta alone. We want to know what theta is equal to. We want to isolate theta. So to isolate angle theta, we have to take the inverse tangent, arctangent. I don't know why I'm using a capital T here. I could just say this is inverse tangent, which is the same thing as saying arctangent. These things mean the exact same thing. That means that it's going to be well, theta equals inverse tangent of y over x. Excuse me, that looks terrible. Hold on, wait. Y over x. And since we have, and so since y is equal to 4 and x is equal to 3, we now know what theta is. Theta is equal to arctangent, inverse tangent of 4 over 3. But what about r, the distance from the origin to the point? How do we find that? Well, we have a 3-4 triangle, a right triangle that we're dealing with. We need the hypotenuse. Well, we can find the hypotenuse using the Pythagorean theorem. Now, the Pythagorean theorem, it goes like this. A squared plus b squared equals c squared, and c is the hypotenuse, the missing side that we need. So the 3 is the adjacent side, so 3 is a. The 4 is the opposite side. 4 can be b. We square them both. That equals c squared. Let's see. 3 times 3 is 9. 4 times 4 is 16. Well, 9 plus 16 is going to be 25. And we want to isolate c, so we'll take the square root of both sides. C equals 5. So from this, we can realize that P, which again is r theta, well, that's going to be r, which is 5, and theta, which is arctangent of 4/3. And these are two different ways to describe the exact same, wait a second. Okay, and these are two different ways to describe the exact same area in space. So I drew out some graphs, and let's analyze them. Let's try to see what's going on. Well, for this first one here, we see that the point r theta, this is true such that r is greater than 0. The distance is greater than 0. The line will come out. The origin is our pole, and what would be the x-axis is now the polar axis. You come out the box looking this way. It starts, you automatically start facing this way. If there's like a person here, right? And you're looking this way. The angle, it's like how much you're looking up, or you could think of it as like if you're shining a laser pointer, and then the angle is how high up you put or where you shine it, with the direction that you shine it. Okay. Now, this graph, the second graph here, it shows this sort of like spiral kind of thing. But it's showing that the coordinates are really, and maybe I'll write this right here, r theta plus 2 pi. 2 pi, it's a full revolution. You did a full circle. Okay? But it's theta plus a full circle. So you come up here, you're at theta. But now you're adding you're adding 2 pi, full revolution, full circle back to that original point that you were at starting at theta. So that's why it's plus 2 pi. But do you remember how we talked about how those circles are concentric? Here are those concentric circles. If you look here at the top right, this is the polar graphing, the polar graph template, and it shows this circle, and then it's inside of this circle, and it's inside of that circle, right? So this is just showing that you're doing the full circle plus theta. So you look at this and you start off at angle theta. You start off at point theta, but then 2 pi is a full circle. So you start off at angle theta and then you do a full revolution and you spin around. This is not showing a jump to the next circle. I don't want to be confusing. This is just showing that you're going from theta and then you're doing another circle around, meaning it represents the same exact point as r theta. You're just adding 2 pi. R does not change. the distance from the pole, it doesn't change. So not to be confused with these concentric circles here. This is a spiral and it kind of comes outward just to show you that it's doing a full revolution because you can't really draw a circle. You can't really draw a circle over itself. So this is to not be confused with a jump from the distance from the pole. It's just a spiral to show that there's a little bit, it's the angle you start at and then a little bit extra, 2 pi. Now, the second, I mean, excuse me, and then this third graph, well, it's showing, it's showing the point r theta and the point negative r theta, and it's showing that they're reflections of each other through the origin. Okay, and then this here is showing that the pxy is the same thing as p r theta, and then I can write out x is r cosine theta. I could just throw some parentheses on there to be neat. Y equals r sine theta. R squared equals x squared plus, excuse me, r squared equals x squared plus y squared. And like we talked about before, tangent of theta is equal to y over x. Oh, and then something that my professor said, which I actually really liked, was that it might seem confusing at first, but the thing is that if you were taught this first, as opposed to being taught the Cartesian coordinate system first, you would look at the Cartesian coordinate system, the rectangular coordinate system, and you would be like, wait, what? So it's just a different way of thinking about it. Let's do an example. So this is a two-part question here. We're asked to plot the points with polar coordinates 2, pi over 6, and -5, -pi. Then we're asked to give two alternative sets of the coordinate pairs for both points. Now, I wrote out P, which is a point in space that's represented by r and theta. We're naming a specific point P, and we're using two numbers, r and theta, instead of using our x and y. So r is the radial coordinates. R describes the directed distance from the center. It's how far that you want to walk from the center, from the origin, how far you walk from the origin. And the angular coordinate, theta, um, it's an angle whose initial side is at the what would be the x-axis, is it's at the positive x-axis. So the initial side I wrote right here. Technically, it's not the x-axis, right? But it's the initial side, what would be the x-axis. Um, and the initial side is where you start every single time. So the angle theta, and we could have it like if you imagine angle theta to be this red arrow that points from the initial side to the terminal side, and that could be the angle. So, um, well, let's see. We have the initial side is a ray, and a ray is part of a line that extends in one fixed that has one fixed starting point, which is called the endpoint, and it extends infinitely in one direction. That's the infinite side. Excuse me, that's the initial side. It extends outward infinitely. Um, and the starting point of every ray is the origin. It's the pole. That's the starting point. You could think of it as like a laser pointer. It's it's uh it's like a you're shooting a laser and it's shooting outward towards point P. Um, the terminal side, well, the word terminal literally just means end, and in trigonometry, polar coordinates, the terminal side is the final position of a ray after it's been rotated. So the initial side, you always start your laser beam pointing along what would be the x-axis, even though technically it's not the x-axis, but to try to gain some like common definition, we could just call it the x-axis, but really it's the initial side. And then the rotation, well, you rotate the beam, the laser beam, And let me just go ahead and grab this red and then just denote angle theta here in red. And that's the rotation. You rotate the beam by angle theta. In the terminal side, it's the position where the beam stops moving, and that's the terminal side. So just note that positive angles are measured counterclockwise, meaning you will turn to your left. So if we're starting at this initial side here, right? Um, and we are working with a positive value, um, the the positive value for theta, that means that um, we're going to go counterclockwise. So if the number is positive, we're going to turn to our left, which is upward from the x-axis, but it's really the initial side, um, really called the initial side, uh, and um, and we're going to go counterclockwise, right? Now, um, if the inverse is true, like if we have negative angles, that means that we're going to go to the right of the initial side, so we're going to go counterclockwise. Um, so we can use this information to try to plot two pi over 6, 2 pi over 6. The starting position, we're going to start on this rectangular coordinate system first to try to plot it, but we're going to start at the initial side here. Um, and the initial side, it's always going to be what we think of as, well, what we used to think of in the rectangular coordinate system as the positive x-axis. That's the initial side. So right here in blue, and over here it's in purple. The rotation, the angular coordinate, um, well, for us, we have angle pi over 6. All right, angle pi over 6. The direction that we're going to go is positive because angles are measured counterclockwise if they're positive. So we need to rotate our view. And one thing that we might want to note, I mean, this is calculus, so we're really working in terms of radians, but if we wanted to take into account our conversion formulas, we could. Right? So if we want to go from degrees to radians, we multiply the degrees by pi over 180. Then if we want to go from radians to degrees, then you multiply the radians. This is multiply the radians by 180 over pi. Let's say that we want to convert pi over 6 to degrees, just to try to sort of just better conceptualize this. Then we're going to do pi over 6 times 180 over pi. These pi's, they're going to cancel. We'll have 180 divided by 6, and 18 divided by 6 is 3. So the answer here, 180 divided by 6 is going to be 30, but it's going to be 30 degrees. So we're going to rotate our view from the initial side. We're going to rotate it upward from the x-axis, well, the initial side. So so 30 degrees, 30 degrees, I think it would be like right about here. And then we can also graph it here on the polar coordinate system, on the polar coordinate system graphing paper. And this is why this stuff is so good, because look, we converted it to 30 degrees. We really didn't have to because, we know our unit circle values, kind of, I hope. And but here it's just given to us. We see pi over 6, and pi over 6 it runs along this line. So we're going to not put a line here. Oh yeah. So so we can draw this line to indicate that this is the angle. This is the angle that we're moving. This is angle theta. And the line that we're now facing, it's called the terminal side. Now, as for the placement, we need to ensure that P is at the 2 unit mark. Because look, here's the thing. R, the distance from the origin from the pole, right? It's 2. Now here's where the graphing paper really does come in handy. Because we have these concentric circles, we have this first circle here, and then we have this second circle here. And then these circles, they go on and on and on. But the first circle is here and the second circle is here. So we got 1, 2 from the pole, and then that means that our dot is going to be right here. That's our point. So really, we could just delete those because the point is only going to come out to right here. And if we wanted to graph this, well, we could try to graph this on here, but there's not really like a way to like count out the circles. We could try to like imagine the circles like 1, 2, and so like we'll say that it's right here, but the concentric circles, they offer like a better unit of measurement and placement for representing P, the point in space. Now, calculating 2 units on the polar grid is about measuring the distance from the center, from the origin. And in polar coordinates, the grid is not, it's not square blocks, all right? So we're not really doing this. We're not really doing this. Like we're working with, we want to do it on this circular graph, on the polar graph. It's not about square blocks. It's made up of concentric circles that act like a ruler for the distance r. So again, just to reiterate, to mechanically find the distance, the center is 0. We're gonna put our cursor here at the origin at 0, and we're gonna count the rings 1, 2, and then we're gonna put our mark here after we've counted angle theta. So we move up from the initial side to represent the angle, and then we count the circles from the origin to place our point R. So we just follow the ray. Once we've rotated to our second angle, we just stay on that specific line on the terminal side, and then we move outward until we hit the second ring, and then we place our point there. So for the first point, 2 pi over 6, this is the standard way to graph. Everything moves in the direction that you would expect. You face the start, right? You face the initial side right here on the polar graph, looking along what would be the x-axis in the Cartesian coordinate system. And then the way that you turn, that's equal to theta, pi over 6. And since pi over 6 is positive, we rotate counterclockwise, okay? And we rotate counterclockwise by pi over 6 radians or 30 degrees. Now you're facing the top right section in what would be quadrant 1. So if we picture this as quadrant 1, we know our quadrants. So in our case, we're facing the top right section at quadrant 1. Now the walk r equaling 2, since 2 is positive, we're going to walk forward 2 units in the direction that we're facing. So 1 circle, 2 circles. And then the point we mark on the spot, we're going to mark the spot, we're going to mark the upper right area, and we're going to do it 2 units from the center. Now, point -5, negative pi is like a lot more trickier. This one got me at first. But if we really focus, I think that we can get it. So it's tricky because it involves 2 reversals. Now r equals -5 and theta equals -pi. And this one's a little bit more tricky. So let's face the start. We're gonna we're gonna face the start here along the initial side, and we're going to look along what used to be the x-axis, the positive x-axis, and now we're going to make a turn. So theta equals negative pi, and since the angle is negative, we're going to rotate clockwise. Pi is equal to 180 degrees. So we're going to, and 180 degrees is a straight line, so we're going to spin halfway around until we're facing um, directly left, and that's going to be, well, that's going to be right over here, what used to be the negative x-axis. So now we're facing this way, okay? But the walk where we're moving is r equals -5. And since r equals -5, and this is crucial, because r is negative, you do not walk forward. You do not walk forward. Towards you walk towards the right because we're going in the negative, we're going negative from this direction, so we're facing this direction, right? But we're gonna walk backwards this way because that's where that's where that's because that's where that's where we're gonna go. Um, Along this line here, starting out from the pole, along this line here, we're going in the positive direction because we've rotated clockwise, which because it's a negative pi, rotated clockwise, all right? We're facing out along this way, but now we're going to turn around and we're going to walk this way because the r is -5. But we're not just going to draw a line. No, what we're going to do is we're going to count the circles. It's -5. So we know that it's going to be like, let's see, we have this circle here. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, right here. And so we're going to put a point right here. Everything else, everything else was just to sort of show the representation of that. So we could just delete all that. And I do believe that these are what our polar points are going to look like. And honestly, we can delete these lines too if we just want to represent the point in space like that. So the walk backwards from the pole 5 units while facing left means that you move to the right, and then the point that we land on, it's across the initial side here, right? At the 5 unit mark, which we count by these concentric circles here. 1, 2, 3, 4, 5. And that's where the red dot is. And now the second part of the question, we're asked to give two alternative sets of coordinate pairs for both points. Well, the problem is about finding the different ways to code the exact same physical location on a graph. So in polar coordinates, you can reach the same spot by spinning around extra times, by engaging in extra revolutions. Um, and you could reach the same spot by spinning around extra times or by facing in the opposite direction and walking backwards. And so there are some mechanical ways, there are a couple mechanical ways to finding alternative coordinates, and so we'll do that for 2 and pi over 6. There's the first way, and the first way is to do like a full circle spin. So we're going to spin 2 pi. So if you're at an angle and you spin exactly in one full circle 2 pi radians, then you end up facing the exact same direction because a full circle, it's 2 pi radians. So we're currently at pi over 6, right? We're currently at pi over 6. But now we're going to do plus 2 pi. Well, plus 2 pi, let's see. It's the same thing as 2 pi over 1. Um, see, pi over 6, we want a common denominator, so what we're going to multiply it by 6. So plus um, 12 pi over 6. That's going to be 13 pi over 6. So this could be another representation for theta, 13 pi over 6. Another representation for theta could be like if we have, let's see, pi over 6 minus 2 pi. That's the same thing as pi over 6 minus 2 pi. No, we're going to multiply by 6, so minus 12 pi over 6. And that's going to be negative 11 pi. I think that's going to be 11 negative pi over 6, I'm pretty sure. Um, and so, well, the result is like, for an example, if we looked at the 13 pi over 6, the result is, well, we could literally say that another way we could describe the point is, wait, 2 13 pi over 6. Which, of course, we could also put 2 negative 11 pi over 6. And we just did an extra lap. It's the same point as 2 pi. It's the same point as 2 pi over 6. 2 comma pi over 6. It sounds like I was saying 2 pi over 6. 2 comma pi over 6. It's the same exact thing. And the other way that we could do this is it's the if we did like a 180 flip and walked backwards. So this is like a case where like if you're facing the opposite direction and then you add pi to the angle. We'll call this a 180-degree flip. So we're going to face the opposite direction and then walk backwards through the origin to land on the target. So we're going to find the opposite direction by adding pi 180 degrees to our angle. So um so the first step here is to take pi over 6 and then to add pi to that, and then that's going to equal 7 pi over 6. And then we could also subtract pi. So if we did like pi over 6 minus pi, that's going to equal negative 5 pi over 6. And then we can walk backward and change the sign of the direction, or excuse me, and then we can walk backwards from this and change the sign of the direction. So what we're doing is like, example, like if we're adding pi to pi over 6, well, we're looking like right here. So we're looking at the green one right now, the green point. Let me see. So it's like symmetrical. It's at the exact opposite point. So we're doing 180, and we're doing it in the clockwise direction. Um, we're doing it in the clockwise direction, which means it's positive. So we're going from here to here. Or I guess we're staying on the circle. So I guess here to here. But that's what the angle's gonna do. But we're going from here to here, and now we're gonna walk backwards. So now what we'll do is we're going to change the sign of the distance from 2 to negative 2. And what's going to end up happening is, well, we're right here, okay, but we're still going to start at the origin here, and we're going to go 1, 2, and we're at the exact same point in green. So, um, so the result could look like this. -2, 5 pi, oh, excuse me, -2, -5 pi over 6. Wait a second. Wait a second. Okay. So the -5 pi over 6 is the case where we're at pi over 6 and then we subtracted pi to get -5 pi over 6. -5 pi over 6. Well, since we subtracted pi, we're going to go -180 degrees, so we're going to move in this direction. But we're going to move from the pole -2 points, so we're just going back to that same point. So this is like another way that we could like code these coordinates into the to the polar coordinate system. Um, then the other way that we could do this is like uh well 2 pi because we switched the sign for r, and then -11 pi. And so that's how you would do that. So to reiterate, for -2 to -5 pi over 6, you rotate clockwise. You rotate clockwise nearly half of a circle, and you are now facing the bottom left. Because r equals -2, you walk backwards, which lands you in the top right at your original spot. For 13 pi over 6, you rotate a full circle plus 30 degrees, and then you're facing the top. You're facing the top right, and you walk forward 2 units, which again is measured with the circles. Okay, so what about alternative coordinates for -5 and -pi? So the thing about -5 and -pi is that there already is a -r and a -theta. And so to find the alternatives, we're going to use the same tricks that we used before, spinning circles or flipping directions. So we can think of this as like where we have an address for something, but we can use different ways to get to that same address. Like there's different streets that you can take. Um, it's gonna get us the same place, r and theta. So for the first way, we'll do this. We'll spin again. So spin 2 pi. This is the full lap, and that's gonna be where you add or subtract 2 pi. And the easiest way is to just spin in a full circle, because you stay facing the same way and the distance stays the same. So we can actually come up with a formula for this. Now that we've done it once and we're going to do it again, we'll just refer to this formula. And then now we can apply this formula to -5 and -pi. So we'll go ahead and we'll add 2 pi. And so if we add 2 pi to -pi, we're going to end up with pi, and then we're going to get, for our coordinates, -5 and pi. And so if we subtract 2 pi, we're going to get -5, and then we'll have -pi minus 2 pi, and that's going to be -3 pi. So our result will be -5, -3 pi. Okay, so let's try to conceptualize what's going on if we add 2 pi on the polar coordinate system. So we start off at the initial side, and let's do it on this one since this one doesn't have anything on it. So we start off at the initial side, right? Here in red. Okay. Then we rotate -pi, and we rotate -pi direction to find theta. So since it's -pi, we're gonna go um we're gonna go clockwise 180 degrees. but then we're adding 2 pi, but we're adding positive 2 pi. So we're actually going to go we're going 2 pi, so here's 1 pi right here, and then here's 2 pi right here. We're doing a full revolution, all right? But we're still along this line here, right? So because r is set to -5, we're not counting from the pole in this direction. No, we're counting to the pole in this direction. So that's gonna look like this. Grab this pink here. We're starting at the pole right here. We're counting the circles 1, 2, 3, 4, 5. And it's going to be right here, which is the same exact spot on this, on that we had graphed it initially. We're just coding the address or the directions to that same address differently. So then for subtracting 2 pi, well, it's going to get us the same place, but it's going to the directions are going to be different. So we're starting at negative. So okay, we're starting at the initial side, right? We're starting right here, in blue, and then we're rotating negative pi. So we're going in the negative pi direction, which is clockwise, 180 degrees. But then we're subtracting 2 pi, which means that we're still going to be moving this way. We're doing a full revolution, and then we're ending up back on this axis here. But again, since the r is set to -5, we're going to go we're going to count the circles 1, 2, 3, 4, 5 in this direction. It's going to get us to that same exact point right there. And then now something else that we can do is we can change r to -r. This is uh this is like if you want to change the sign of the distance of r, we have to face the exact opposite direction so that walking backwards is going to put us back into that original spot. And we'll create a formula. We have a formula for this, and there's two. So the first thing that we'll do is we're going to change r from -5 to 5. So r now becomes 5. We're changing the sign. And then the second thing to do, well, the second thing to do is to add pi to the angle. So we'll have -5 plus pi. Okay, and that's going to equal 0, and that's our new angle theta. Um, but now our result for this is going to be 5 and 0. Um, but so no, if our angle is 0, we're not moving anywhere. Here's 0. We're not moving anywhere from 0, but we're still going to count out from the pole in the positive direction. So we're going to count these circles 1, 2, 3, 4, 5, and now we're in the same exact spot as we were before. All right. Now there's a third uh, there's a third way that we can do this, and this is called the negative angle spin. So if you have a positive angle and you want a negative one or vice versa, um, you find a gap. You find 2 pi. So the logic here is that if you are at pi, you're halfway, going the other way around the circle is also pi. So since the original was negative pi, which is clockwise, the opposite direction uh, is to go counterclockwise. So for our different values, we can have 5 and 0, and want to go, if you want to do the negative angle spin, well, then we'll have 5 and pi. And these are different ways that we can um, show the exact same point in space by using different directions. Let's talk about the calculus on polar equations. The slopes of tangent lines for polar curves. If we let f be a differentiable function at theta sub 0, then the slope of the line tangent to the curve r equals f of theta at the point f of theta sub 0 and theta sub 0 well, that's going to be dy over dx. It's going to be the derivative of y with respect to x, and that's going to equal, having applied the chain rule, that's going to equal um, r prime of theta times sine of theta plus r of theta times cosine of theta. And then in the denominator, we're going to have r prime of theta times cosine of theta minus r of theta times sine of theta, provided that the denominator is non-zero at that point. And then here's a little visual. Here's a little visual of what's going on. We can see the tangent lines for the curve r equals f of theta. And then this is how you calculate the slope. I know that this looks a little bit intimidating, but if we work through a problem, it actually comes together very nicely. So let's investigate this problem here. It says find the slope of the line tangent to the cardioid given by r equals 1 plus cosine of theta at the point theta sub 0 equals pi over 3. Well, if we were to graph this curve, it would look something like this. This is not drawn to scale, guys. I'm not gonna pretend like this is drawn to scale. I can't. There's no pretending. I mean, look at it. It's not drawn to scale. But right here at this point of intersection, right here, um, I'll put a little dash here. This is gonna be 2. Pretend that this is like intersecting right here. It's gonna be intersecting at 2, and then well, we're gonna have a crossover here at -1. Over here, the origin or the pole. This is the pole at this point because this is polar coordinates. Um, is going to be 0, 0. And then right here, up here, it's going to be 1. All right. And so here, r equals 1 plus cosine of theta. All right. And we're looking for the slope. We're looking for the slope, you guys. So this is going to be m sub t, and the point is theta sub 0. So we'll put a theta here, and we'll say that this is the theta sub 0 is set to pi over 3. All right. Now, I'm just going to click back to this. We have here the formula for finding our slope. Okay. So we'll go ahead and we'll grab this blue, and I'm just going to write it out. This is how we can find our line tangent to the cardioid for this polar equation. Let's just start running through this. The first thing that we should do is we're just going to establish that r of theta equals 1 plus cosine of theta. All right? That's what r is set to. And we know what theta is because it's pi over 3. So, well, that means that we can plug in our pi over 3, and that's going to equal 1 plus cosine of pi over 3. Just plugging in pi over 3 where theta is. Okay? And, well, there is something called special angles. There are things that are, there are special angles that are called special angles. And and when we look at cosine, of pi over 3, it's equal to 1/2. And so, let's see, this is a special angle. And there are a few special angles, trigonometric angles, um, for mainly tangent, well, sine of theta, cosine of theta, and tangent of theta, which is sine over cosine. And it's I'm not gonna sit here and tell you guys to memorize them because, quite frankly, I keep a note card at my desk with them on it. Um, Now that said, this function is gonna transform. It's gonna become 1 plus 1/2. And then we can rewrite 1 as 2 over 2 plus 1 over 2. It's going to be 3/2. What about r prime of theta? What about r prime? What about its derivative? Well, we can't just take the derivative of 3 over 2. We have to take the derivative of this function here. In other words, we're going to find the derivative of 1 plus cosine of theta. And, well, that's the same thing as the derivative of 1 plus the derivative. That looks a little bit wonky, doesn't it? There you go. So that's the same thing as the derivative of 1 plus the derivative of cosine of theta. So the derivative of 1, it's going to be 0 because the derivative of a constant is always going to be 0. So we'll have 0 plus, well, the derivative of cosine of theta, or the derivative of cosine of x, whatever you'd like. This is going to be, I do believe it's actually negative sine of theta. It's negative sine of theta. And so then this is the derivative of that. Well, we're just gonna write it as negative sine of theta. But then remember, like we know what theta is. So we'll go ahead and we'll just write negative sine of pi over 3. And then same sort of thing. This is another special angle, I believe. It's um, so sine of theta, sine of sine of pi over 3 is going to be root 3 over 2, but there's a negative in front of it, so it's going to be negative root 3 over 2. And then special angles are a little bit tricky, but I'm actually, after I finish this video, I think I'm going to record a video on the unit circle and talk about special angles a little bit there and parametric equations. But I digress. Let's go ahead and we're going to continue forward with this. So we have what we need at this point, right? We got 1, we got 1, then we got 2, 2, and so we can just plug that stuff right on in. So let's make this a little bit neater. We know that, well, let's just sort of get everything right here. We're just gonna kind of gather everything up, get our bearings straight, get everything, sort of sorted out and neat. So it's gonna be 3 over 2. R of theta is 3 over 2, or 3/2. And then r prime of theta, well, that's gonna be negative root 3 over 2, because that's what we actually found it out to be. So here's what we have, right? Okay, r prime of theta, check. We got that. R of theta, check. We got that. Okay, but what's sine of theta? What's sine of theta? What's sine of pi over 3? Well, if you remember from earlier, we calculated it. And let's see, where did we calculate it? Sine over 3 right here. That we technically we did negative sine over 3, but now we're just doing sine over 3. So we could just strip away that negative sign, and this is going to be another special angle, by the way. Root 3 over 2. And then we need cosine of theta, which is another special angle, which we already calculated, but um, let's see, cosine of theta, which is really cosine of pi over um, excuse me, uh, cosine of pi over 3. And that's going to be cosine of pi over 3 is 1/2. And honestly, I'm just going to like put this in a little box. I'm going to put this in a little box here because you know, I don't want to get confused. Now we have everything that we need to plug in to our formula. So I can write out dy over dx, and we're looking at theta here. And theta is set to pi over 3. So at this point, we just have to plug into our formula to find the line tangent. So namely m sub t, but uh, we know what everything here is. R prime of theta is going to be root 3 over 2. No, negative root 3 over 2. Sine of theta is going to be root 3 over 2. Then we're going to do plus r of theta, which is going to be 3/2 times cosine of theta, which is going to be 1/2. This is going to be all over prime r prime of theta, which is going to be a negative root 3 over 2 times cosine of theta, which is going to be 1/2 minus r of theta, which is going to be 3/2 times sine of theta, which is going to be root 3 over 2. Wait, then we can simplify this and we'll start here. But one thing to note is that if you have like root and times a root, well, that's the same thing as root 3 times 3, both with a radicand over it. Um, and then that's the same thing as the square root of 9. Square root of 9 is 3. There's a negative, so we have to be careful. Um, well, so if we simplify, this is going to be negative 3 over 2. Nope. Negative 3, we have to multiply these denominators together, which is going to be 2 times 2, which is 4. So we get negative 3/4 plus 3 times 1, which is 3, over 2 times 2, which is going to be 4. So we end up in the numerator with negative 3/4 plus 3/4. All right. Then we have negative root 3 over 2 times 1/2. Well, that's going to be negative root 3 over 4 minus 3 times root 3, which is just going to be 3 times root 3. And then 2 times 2, which is 4. I'm going to rewrite this. We got 0 in the numerator. Negative, we're going to put a negative 1 in front of that root 3, that first root 3, minus 3 times root 3 over 4. And perhaps it will be a little bit easier to see what's going on because we can combine this negative 1 and this negative 3 so that we have negative 4 root 3 over 4. Of course, these 4's are going to cancel out. Well, not the negative, not the negative's not, but the 4's are. And then this is going to be 0 over negative root 3, but that's just going to simplify out to be 0. So what that means, and I know that I didn't have to show all the math for that. I just was like getting tripped up over it, so I want to make sure that I'm clear on that. That's how you get it to be negative root 3. So that's just for my own preference, but that means that the answer to this, the slope of the line tangent to the cardioid for that curve is going to be it's going to be equal to 0. But what if we wanted to find the area inside of the cardioid? What if we wanted to calculate the area that's inside of this? Moreover, I might even mention this. Why is this even important? Three words. Spherical coordinate system. Now let's say that I want to find the area inside of the cardioid. I want to find the region inside of here. Like I want to find like what's the area inside of this cardioid. Well, to do that, we need to understand how we can find the area of a region within polar coordinates. And so I have a little formula here for you guys, a little picture I drew out. It's not the greatest, but hopefully it can show that R is the region that's bounded by the graphs of f of theta and g of theta. And it's between theta, which is set as alpha, and theta over here, which is set as beta. Where f and g are continuous, and maybe I should mention that f of theta is to be greater than or equal to g of theta, which is to be greater than 0. That is greater than or equal to 0 on the point alpha beta. The area of R, it can be found by taking the definite integral from alpha to beta for 1/2 times f of theta squared minus g of theta squared, integration with respect to theta. So we have our cardioid here, and we're prompted to find the region inside of the curve 1 plus cosine theta. But where did our formula go? Not to worry. I'm going to look at this formula here, and I'm going to slightly tweak it, because as you can see, we're not dealing with two separate explicit curves. We're looking at the shape of the cardioid on the axis itself. So I'm going to alter it slightly. So what we're doing is we're taking R and we're squaring it. And R is set to 1 plus cosine of theta. So this formula can be used to plug in for what we have. A will stand for area. Now at this point you might be wondering why the upper bound of integration is 2 pi. The reason is because 2 pi is 360 degrees. 2 pi is a full revolution. And in this particular curve, it takes 2 pi to go all the way around it. So if you think about a unit circle, to do one full revolution, it's going to equal 2 pi. All there's left to do is integrate. So I'm going to go ahead and factor out that 1/2. And so at this point, I'm pretty sure that here we can apply a plus b squared equals a squared plus 2 times a times b plus b squared, such that here a is set to 1 and b is set to cosine of theta. Gosh, so this is going to be 1 squared plus 2 times 1 times cosine of theta plus cosine of theta squared, integration with respect to theta. What needs to be done next is that we need to take into account that cosine squared, cosine of theta squared is the same thing as 1 plus cosine of 2 theta, I think, over 2. This is called the power reduction formula because it reduces the power. It's called something like that, but whatever it's called, it's true. And we'll go ahead and we'll apply it. Well, 1 squared is going to be just 1. We'll have it plus 2 sine, 2, excuse me, 2 times cosine of theta, um, plus the right side of the angle reduction formula. It's unofficial slash official name. To be honest with you, I can't remember. But I know this is true. 1 plus cosine of 2 theta over 2 integration with respect to theta. I'm going to rewrite this. 1 plus 2 cosine of theta plus 1/2 plus cosine of 2 theta over 2 integration with respect to theta. So this is its own separate entity. This 1 is its separate. Well, it's not its own separate. Okay. Basically, I can make this 1/2, and then I can make this cosine 1/2 cosine of 2 theta, and I will do so. So all I'm going to do is I'm just pulling that 1/2 out front for the cosine of 2 theta. But the reason for that, never mind this for a few seconds. I just have that ready for when I write something in. But because I rewrote this, um, I disconnected this 1/2. Well, you watched me disconnect the 1/2, and then I brought that 1/2 out front for the cosine times, or excuse me, for the 1/2 times cosine 2 of 2 theta. And I did, but I brought this 1/2 out front because I wanted to combine like terms. I wanted to combine like terms with this 1 because I can rewrite this as a form of 1, 2 over 2 plus 1/2, and this is going to equal 3/2. And I'm going to write that 3/2 in blue just so we can see what's going on. So you're not like, well, where did that 3/2 come from? Because when I first saw this, I was like, what? So I just want to be very clear. But then we'll just continue onward with this 2 times cosine of theta. And then now this 1/2, well, it's not gone. It's just it's just of a different form. Um, but now we're just going to add 1/2 times cosine of 2 theta. Well, then this is integration with respect to theta. Well, at this point, I think the move is probably to just integrate. We're just going to integrate. Um, well, and so that's going to look like this. The area is equal to 1/2, and then let's integrate our terms in these brackets here so that this 1/2 gets distributed to each term. So the integral of 3/2, well, 3/2 is a constant, so this is going to become 3/2 theta. The integral of 2 cosine of theta, well, if we want to anti-differentiate, we'll go ahead and we'll factor out that 2 for just a second. And then we'll just take the integral of cosine. And the integral of cosine is sine. And then we'll multiply back that too. So our result after anti-differentiation will be sine of theta. Same sort of deal here with one half, this 1/2 times cosine of 2, excuse me, 1/2 times cosine of 2 theta. But this one's a little bit more tricky, so I will write out a formula for this. Um, well, let's see. The integral of cosine with a coefficient, integration with respect to the variable that we're integrating with respect to, equals 1 over a. So that coefficient goes into a denominator in a fraction that's out front, sine of a times x. Well, and this technically, look, there's not going to be an arbitrary constant because this is a definite integral, but I'm just going to add the plus c because, you know what, I just am. I just am. Just so we don't forget, just because I didn't specify here. Um, but that's technically not needed. I mean, you could put it, but it's technically not needed because this is a definite integral. I'm going to get a swig of water. So now that we've established that, we're gonna, well, first we'll factor out that 1/2 just for a second. We're gonna take the integral of cosine of 2 theta. Well, we're gonna bring out that um the coefficient 2, in this case, it's gonna go to the denominator. Then we're gonna integrate cosine, which is just gonna be sine, and then what's in the parentheses stays the same, 2 theta. Integration with respect to theta. Oh, we don't have to do that anymore. Sorry, we just integrate. Whoopsies. Okay, wait. And then this is going to be integration, or excuse me, the evaluation bar, evaluated from 2 to pi, excuse me, 0 to 2 pi. However, that's going to become 1/4. So just go ahead and specify. At this point, I'm going to evaluate what's inside of the brackets. I could distribute, but I think I'm just going to evaluate what's in the brackets. Um, really quickly, and we'll do this using the fundamental theorem of calculus part 2. And what this is telling me to do is it's telling me that everywhere where I see a theta, I'm going to plug into pi. This is the upper bound of integration. But the fundamental theorem of calculus says that we have to subtract what we get when we plug in the lower bound of integration. So let's go ahead and do that. And that should just about do it. Well, at this point, there's going to be a lot, and I mean a lot of cancellation. So sine of 0 is 0, times 1/4 is 0, so this whole term goes to 0. Now sine of 0 is 0, times 2, well, that's also 0. 3/2 times 0, that's 0. Um, well, sine of 4 pi, if you think about this here, let's look back at our unit circle, right? The unit circle has a 0 right here. One full revolution, 2 pi, well, that's also 0. Another full revolution, 4 pi, is also 0. So, well, this whole term just goes to 0. As we've established, or just to be direct, we know that sine of 4 pi is 0, and 0 times 1/4 is 0. And then the same sort of thing here, where 1 full revolution is 2 pi, so you're going to be at the 0 point. Therefore, sine of 2 pi is 0, times 2 is 0, because 0 times 2 is 0. All right. What about this 3/2 times pi? Well, this 2 is going to cancel with this 2. Now we have 1/2 times 3. Well, 1/2 times 3, that's going to be 3/2. Oh, but we're not done because this 2 only canceled with this 2. It didn't cancel with the pi. That pi is still intact. That means that we're going to multiply this thing by pi. And that means that our area is equal to 3/2 pi, which can be approximately, which can be approximated out to be 4.712. And that's our area. So that's how you find the area inside of a cardioid. Let's do another problem. I chose this problem because I think that it exemplifies calculus and polar coordinates and all of its beauty in a way that's very ideal. It says to find the slope of the line tangent to the polar curve at the given points. R equals 3 times cosine of 2 theta at the tips of the leaves, and find the derivative of y with respect to x as a function of theta. If you remember from earlier, we came up with a rule when it comes to graphing flowers. I mean, I didn't come up with it, but we've established it in this video. The petals represented in sine and cosine functions are, the number of them are dependent on the coefficient in front of theta. So if the number is even, which in this case it is, we're going to have double the amount of the coefficient. So in this case, there will be 4 petals. The graph will look like this. When it comes to finding a slope of a tangent line for a polar curve like this, which is again a 4-petal rose or a 4-leaf rose, it requires a few more steps than standard calculus because you have to translate polar logic into the XY coordinate system. So the first thing to do is we're going to write out the derivative formula. And we're going to use the chain rule since x and y are both functions of theta. First things first, we have to use our conversion identities, namely x equals r cosine of theta and y equals r sine of theta. So into both of these, we're going to plug in 3 cosine of 2 theta. So this is a bullet point here, but this is going to be, well, x equals 3 cosine of 2 theta times cosine of theta. Here's another bullet point. Well, and this is going to be y equals 3 cosine of 2 theta times sine of theta. And well, at this point, it's crucial for us to plug in the product rule for differentiation. dx over d theta means the derivative of x with respect to theta. And we're gonna start by um, substituting in for our equation for r. That is x, and this is just the same thing that we wrote up there. X equals 3 times cosine of 2 theta times cosine of theta. Now on this channel, we investigate patterns. So this here can be f, and this here can be g. And that's great, because then we could say that, all right, well then, let's get started on breaking down this product rule. Set f of x equal to 3 cosine of 2 theta. But the thing about this is, when we go to take this derivative, when we go to take f prime of x, well, that means that we're taking the derivative of 3 cosine, of 3 times cosine of 2 theta. All right, well, let me make that a little bit neater, because this here, guys, this requires the chain rule. And we know that this requires the chain rule. Chain rules differentiate the outer function and multiply it by the derivative of the inner function. Of course, this requires us to identify what the outside function is and what the inside function is. So the outside function, we're going to call this f of u. And the outside function, f, is going to be 3 times cosine of u. All right, so then the inside function is going to be, what's u, right? So the next step is to find f prime of u. How can we find f prime of u? Since f of u is set to 3 cosine of u, that means that we are required to know the derivative for cosine of some variable. So we'll just write out the derivative of cosine of x. I believe it's negative sine of x. And then for us, that means that, well, we'll factor out that 3 for the time being. Take the derivative of cosine of u, and then, well, then we'll get negative sine of u, and then we'll multiply back that 3 to get negative 3 sine of u. So then to get this part here, f prime of g of x, we'll just substitute back in for u. So f prime of g of x, the first part for the chain rule, well, that's going to be the derivative of f prime of u, so negative 3 times sine of u, but instead of u, we're going to put back our 2 theta. Okay, but then we have to find the derivative of u. For specificity, we could just say, all right, u prime, that's the same thing as g of x. So u prime, aka g of x, right? Inside, let's say that's also known as g of x. Well, if we want to find, um, well, say, maybe that's not true. Maybe I should say, okay, yeah, right. Um, g prime, g prime of x. U prime, also known as g prime of x, well, that's going to be to take the derivative of what we've set g of x or u to. Again, I'm using those synonymously, so we want the derivative of 2 theta. Well, that's the same thing as factoring out that 2, taking the derivative of theta, which is just going to give us 1, I think, equals 2 times 1. This is going to equal 2. So g prime of x, or u prime, is going to equal 2. And so what that means is that, well, the derivative with respect to theta for 3 cosine of 2 theta, well, that equals, oops, where's my bracket? Well, that equals -3 sine of 2 theta, all right, times the derivative of g prime of x, u prime. So that's what we found to be 2. Okay, and then that's going to result in -6 sine of 2 theta. Okay, but now, at this point in time, we need to find the derivative of y with respect to theta. And, well, we're going to use our identity. Y equals um, r times sine of theta. And, well, we're just going to substitute r into that. Right, so we're going to get y equals 3 times cosine of 2 theta times sine of theta. I know, and because this requires the product rule. This is a product. Um, and well, we have the product rule right up here. And so if we let 3, let's do this, 3 cosine of 3 times cosine of 2 theta, well, that can be our f sine of theta, or that can be our g. And well, we're just gonna go through with that product rule. We have f of x. You can even say that this is just f of x, f of x and g of x. Well, that means that we need to find our f prime of x. F prime of x, by definition, is the derivative for 3 cosine of 2 theta. And then what to do? Well, factor out that 3. And then we leave this cosine of 2 theta. Now, taking the derivative of cosine of 2 theta is a little bit different than what we have up here, but I do believe it goes like this. So it's not just cosine of x, it's cosine of ax. Let a represent some sort of coefficient. The derivative of cosine of a times x, let a represent a coefficient. That a is just going to come out front, but the derivative of cosine turns into a negative sign. So it's going to be negative a times sine of a times x. Let's just work through this then, because the application of this, it's going to be like 3 times -2 sine of 2 theta. That equals -6 sine of 2 theta. All right, then we're going to have to get worked on that g prime of x. Okay, so g of x is set to sine of theta. And, well, the derivative of sine is cosine. So g prime of x is going to be the derivative of sine of theta. And that equals cosine of theta. And then we can go ahead with the application of our product rule. We should be good to go. So let me be very specific. The derivative of y with respect to theta equals f prime, which we found to be -6 times sine of 2 theta. And then we have to multiply that to g, not g prime, just normal g. So sine of theta plus normal f, 3 cosine of 2 theta. And then we're going to multiply this times cosine of theta, because that's what our normal g is set to. No, excuse me, that's what our derivative of g is set to, g prime. That's what we found it to be. And then with a little bit of simplification, we're going to get -6 sine of 2 theta times sine of theta plus plus 3 cosine of 2 theta times cosine of theta. And I screwed something up. I never plugged what we had back into the product rule, because this is a product rule application. Ah, gosh, I can't believe that's so messy. I can't believe it. All right, it's okay. I'm not gonna dwell on it. Um, so it's gonna be f prime of. So what do we get for f prime? No matter though. For f of x, we set it as 3 cosine 2 theta. Okay. What's f prime of x? Well, that was the issue, and so we went and we solved that. We factored out that 3. There it came out. And oh, yes, times 2. And now that's where that 6 came from. And that's where that 6 came from. Okay, so then f prime of. Okay, then the g of x, that was going to be cosine of theta. G prime of x, that's just going to be negative sine of theta. All right, so here's what we didn't do. before right here is when I moved on. I sloppily moved on to um, the derivative of y with respect to theta, and I just didn't plug back into the product rule, which is what we had spent this entire time here and this line up to here setting up for and doing. So here's what the actual application of the product rule is going to look like for the derivative of x with respect to theta. Well, it's going to be negative. The application of the product rule is going to be with the derivative of x with respect to theta is going to be -6 times sine of 2 theta times cosine of theta plus a negative, right? Not a negative. Oh, almost a negative. Well, it could be. Hold on. Let's just see what happens. Let me not get ahead of myself here. Plus 3 cosine 2 theta times um uh negative sine of theta. And we're gonna go with the simplification here. Negative sine of 2 theta. No, -6 sine of 2 theta times cosine theta minus, I'm just going to bring this negative sign out front, right? Yeah. Minus 3 cosine. No, something's messed up again. Okay. -3 cosine 2 theta. That does not look like a theta, does it? 2 theta sine of theta. This is the derivative of x with respect to theta. Now, we can plug in for the slope. So let me just be thorough. dy over dx equals dy integration of y with respect to theta over integration with x with respect to theta. Okay. Um that's gonna be -6 sine of 2 theta times sine of theta plus 3 cosine of 2 theta times cosine. That's like a backwards 6, dude. Cosine of theta. This is going over what we have just calculated, negative -6 sine of 2 theta times cosine of theta minus 3 cosine of 2 theta times sine of theta. Now, for aesthetic purposes, it might serve us, and even just, I don't know, if we want to put them like in a descending, if we want to put them like the coefficients descending, we could write 3 cosine of 2 theta times cosine of theta. Sorry guys, it's kind of hard to write fast because I got a mouse. But also maybe it's good for information retention, right? Who knows? Minus sine of 2 theta. Uh-oh, I gotta go down here. I gotta, hold on. Negative focus. Negative, okay. Sine of theta. And then this is gonna be all over negative 3 cosine of 2 theta. Oops. Negative 3 times cosine of 2 theta times sine of theta minus 6 sine of 2 theta times cosine of theta. There we go. Let me just double check everything. Well, so this here is our beautiful slope. All right. So now we want to find the slope of the line tangent to the polar chord at the tips of the leaves of 3 cosine of 2 theta. Now finding the slopes at the tips of the leaves, our four petaled rows here, our 4 leafed rows. Well, it has its tips where R is at its maximum and minimum. This happens at, well, it happens when theta equals 0, pi over 2, pi, 3 pi over 2. And well, well, I don't know if I have room. That's okay. Think about the unit circle. We got 0, pi over 2 up top. That corresponds to the tip here of the line. We got pi over here, and we've got 3 pi over 2. And you can bet that this is getting moved over here. Oh no, is there no room? Good. Okay, I'm scrapped for space, you guys. Just squeeze it in down there. Oh no, the tip of my pie. Wow, that thing got truncated. Wait. All right, you get the idea. So basically, um, well, the derivative formula that we have is like a slope machine, right? You feed it an angle, you give it a theta, you give it an angle, and it tells you if the curve is going to go up or down. Or it even tells you if it goes straight at that exact spot. So let's plug in some values. All right, first let's investigate, and I'll put a 1 here. Like um what happens uh at 0 when theta equals 0? This is going to be the right tip. What happens? Well, at the top, we're plugging in for 0, and we're plugging this into the numerator of our slope machine, right? So we got a 3 cosine of 0 times mm, times cosine of 0 minus 6 sine of 0 times sine of 0. Okay, that's gonna be um that's gonna be the same thing as 3 times 1 times 1, which equals 3. Hmm. So I'm gonna just put a 3 here, and I'm gonna utilize this space. What about at the bottom, the denominator? Oh, we're gonna plug in, let's see, negative 3 cosine of 0 times sine of 0 minus 6 sine of 0 times cosine of 0. Um, that's gonna be 0 minus 0. This is gonna 0, this is gonna 0, that's gonna be 0. Okay, that means that we are gonna get 3 over 0. But what's 3 over 0? That's, I don't know if I could write this really tiny. Undefined. Undefined is that's a vertical slope. Undefined is a vertical slope. Basically, we have 3 divided by 0, which is undefined, right? If it's undefined, that means that there's a vertical slice. We're looking at what happens at 0, when theta equals 0. And we know from our unit circle that that's going to happen at the right side, um, at the right side. And so we're looking at the right tip of our pedal. And the right tip of the pedal is when we plug everything in to our slope finding formula right here. Um, but we got something that's undefined, which is a vertical slope. And the vertical slope is going to be right here. Now, my computer is bugging out right now. I don't know what's going on, but I'm going to restart it and end the recording. And when I get back, we'll investigate what happens when when theta equals pi over 2. So the top tip, we're going to find the slope right up here. All right, we're back. So let's put a 2 over here. And let's plug in values. So let's do the numerator of the fraction. 3 cosine of 2. 3 cosine of 2 times pi over theta. No, pi over 2 times cosine pi over 2 minus 6 sine of 2 times pi over 2. Well, that's going to equal, let's see, we're going to get 3, because these 2's are going to cancel, and these 2's are going to cancel. Oh yeah, hold on. You got another sine. That's actually going to be times sine over, excuse me, times sine of pi over 2. And what's going to happen? Well, cosine of pi is -1, right? We're doing this at the top. Cosine of pi is -1. So what we're going to have is 3 times -1 and then cosine of pi over 2 is 0. And then sine of pi is 0. So it's literally going to be 3 times -1 times 0 minus 3 times -1 times 0 minus the sine of pi is 0, so it's going to be minus 6 times 0, and then sine of pi over 2 is 1. And then this is just going to be 0, because this is going to go to 0. That's going to go to 0. This is going to be 0 for the numerator in this case. And then the denominator, let's do bullet point bottom. Well, we're plugging in pi over 2, so -3 cosine of 2 times pi over 2, same thing as before. Those 2's are just going to cancel, so it's just going to be cosine of pi times sine of pi minus 6 sine of pi, because the same thing as before, 2 times pi over 2 is just going to be pi. Cosine times cosine of pi over 2. Well, we're going to get at the beginning there, cosine of pi is -1. So it's going to be -3. So start off with a -3 times the cosine of pi, which is -1. Um, Sine of pi. Is it sine of pi? No, it's sine over pi over 2. I don't know why I put a 2 there. I mean, why I didn't put a 2 there. This is sine of pi over 2. I don't know why. I don't know why I didn't put a. No matter. Sine of pi over 2. Well, sine of pi over 2 is going to be 1. So it's going to be -3 times -1 times 1 minus, well, 6 times 6 times sine of pi. Sine of pi is 0. So that's going to be 0. Cosine of pi over 2 is going to be 0. So 0 times 0 is 0. So we just literally minus 0. Well, the answer to that, it's going to be 3. And so the result, it's going to be 0 over 3. And that 0 over 3 is 0. And that's going to be our slope, which is going to be, um, I might as well just write it up here. Horizontal. Sorry, I know my handwriting is kind of atrocious. I'm just kind of scrapped for room. I know my handwriting's atrocious. I just, you know how it is sometimes. But, so, okay, so that means that the slope is 0. That means the slope is going to be horizontal. So at the top tip, let's do a different color for the slope. Well, let me just do an arrow indicating that this is for that. Okay, yeah, I mean, like, we could do, like, I don't know, guys, what color are we feeling? I feel like we could do, like, some sort of blue or something like that. Um, so, two, I'm gonna do this in blue. So, slope at the top tip, which is horizontal, guys. And that's the tangent line. The slope of the line, that's the slope. Okay. Um, all right, and let's keep the ball rolling here, and we're gonna go after 3. Um, just a quick note. It's like rise over run. It's like rise over run. Vertical change over horizontal change. The slope of 0 is always going to be horizontal. An undefined slope, it's always going to be vertical. Now, let's just see what's going on. Technically, these are symmetrical, so we don't have to do this, but I like to do this because it's just like it helps me see the patterns. So let's see what's going on at theta when it's just set to pi. Um, and this is going to be the left tip of the leaf, and it's going to be leaf petal, whatever you want to call it, but it's going to be over here. So we're looking at this guy now. That said, let's go through with the analysis of the numerator, and that's going to be 3 cosine of pi times cosine of pi minus 6 sine of 2 pi times sine of pi. Well, well, cosine of pi is -1. Oh, but first we need to take into account that 3. So we're gonna have 3. Oh, shoot. Okay. I'm sorry, you guys. I don't know why I wrote cosine of pi. It should have been cosine of 2 pi. 2 pi. Cosine of 2 pi, right? Okay, well, yeah, so we're starting off with a 3. 3 times cosine of 2 pi. Well, cosine of 2 pi is 1. Um, cosine of pi is -1. Minus 6 times Sine of 2 pi. Sine of 2 pi is 0. Sine of pi is 0. So it's just going to be, well, 6 times 0 is 0. Yeah, so 0, 0. This is just going to be 0. Um, that was like a 6, 0. Um, well, that means that we're going to have -3. All right. Um, well, let's do the bottom. This is the denominator here. So it's going to be -3 times cosine times, it's going to be 2 times pi um, times sine of pi minus 6 sine of 2 pi times cosine of pi. All right. And well, 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 sine of pi is 0. So we're going to have -3 times 1 times 0, which is going to be 0, minus 6 sine of 2 pi. Well, sine of 2 pi is 0, so we're going to have 6 times 0 times um, cosine of pi is -1, but -1 times 0 is just 0. So it's going to be 0, the result. And so that means that we're going to have, uh, that means that we're going to have -3 over 0. And that's going to be undefined and vertical. Undefined and vertical. So, yeah, we're going to have a vertical slope right here. Yep. And let's do the last one. Let's do the last one because the last one it's going to be well, we're gonna investigate what happens at theta equals 3 pi over 2. 3 pi over 2. And well, that's going to be the bottom tip right here. Oops, right here. So we're looking at the bottom tip of the petal right here. And so, yeah, guys, and so let's just jump right in and let's just see what's going on. You know, I mean, we already kind of know what's going to happen. It's going to be horizontal, but that's okay because we're just going to plug in anyway. That's what matters. So 3 times cosine, um, this is going to be 2 times 3 pi over 2, but those 2's are just going to cancel. So we're just going to go ahead and stick a 3 pi in there. Um, times cosine of 3 pi over 2. Um, minus 6 sine. And then those 2's are going to cancel. We're going to have minus 6. No. Yeah, actually. Minus 6 sine of 3 pi times sine of 3 pi over 2. And then, well, that's just gonna equal, I mean, yeah, that's gonna, okay, because like, let's see. Yeah, yeah, right? No, 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 this is wrong. This is wrong. This is supposed to be, because we're doing the top one. Oh no, wait a second. Cosine of 3 pi over 2 is gonna be 0. I'm pretty sure. Let me just check it. Yeah, it's 0. So that's 0 times anything is 0 minus, well, 6. I'm pretty sure sine of 3 pi is 0. Yeah, it is 0. So it's just gonna be 0 minus 0, guys. It's gonna be 0. Um, okay, and then let's see what's going on with the bottom. And then the bottom is gonna be, well, -3 times cosine of 3 pi over 2. Um, no, no, it's not. Three, yeah, because those twos are going to cancel. So it's actually going to be negative 3 cosine of 3 pi, times sine of 3 pi over 2 minus, 6 sine, of 3 pi. Same thing is going to cancel, but it's going to be 3 pi, uh, times cosine of 3 pi over 2. All right, and let's just do some analysis because -3 times, let's see, cosine of 3 pi is, so it's going to be, 3, oh, excuse me, it's going to be 3, no, yeah, it's going to be -3 times -1. -3 times -1 times -1. Wait a second. Wait a second. What? Sine of what? Sine of what? 3 pi over 2. Yeah, it's -1. That's very peculiar. Oh, wait, no, actually, that makes sense. Okay, fine. Yeah, that does make sense. -3 times -1 times -1 minus -1. So the -3 is going to turn positive for a second, then it's going to go negative again. Then you have -1. Wait, what? Wait, what is going on with this? Sine of 3 pi is 0. 0 times, well, anything is going to be 0. Okay, yeah, so it's actually going to be -3 times -1 times -1 minus 0. And so that's going to be -3. And so our result, well, the slope is going to be Zero divided by -3, which is going to be 0, and that's going to be horizontal. And since we did blue for the other horizontal one, for the symmetrical piece there, we'll do blue again. So that's our slope, and we'll just do it like that. And so, like, what does that mean? Like, what, like, okay, like, what are our results? So, in conclusion, in conclusion, um, well, that means that the slope is undefined at 3 comma 0, the point 3 comma 0, and 3 comma pi. But the slope is 0 at the points -3 and pi over 2, as well as the point -3 and 3 pi over 2. And so that's our conclusion, guys. So I think that's gonna wrap up the polar coordinates video. I appreciate you guys for watching, and good night and good luck.